So as a part of this common probability distributions which we started the last week, we looked at two discrete distributions, the discrete uniform distribution as well as the binomial distribution, where we looked at the probability of occurrence in each of the cases, and even how do we find out the mean as well as the variance in case of binomial as well as the uniform distribution. Now, the one application of binomial distribution which is more prevalent in the finance community, which is more pertaining to decision taking. So a decision tree. There is always a possibility. Let's say we talk about stock price movement. Assume that the initial stock price is some S. The next day, it can either go up or go down. There is some chance, probability, that it will go up. There is some chance that it will go down. Same thing with the second day, right? Suppose it has gone to US up on the first day. Probably it can again go up to US 2 times up, or it could have come down. The same thing could have happened if it has gone down on the first day. It could have risen or it could have fallen. Now, this is a very common application in a lot of financial aspects, both for stock price forecasting as well as working out on various stock related instruments like derivatives and all. These fundamentals are used to a large extent. And what are the things which we are using here? One, a probability of going up. So if it does not go up, it will go down. Right here, assuming that it will not stay at the same price. So if P is the probability that it will go up, 60% is the probability that it will go up, 40% that it will go down, which is nothing but 1 minus P. So that's where I put 1 minus P as a probability that it will go down. And similarly, at every place, if I assume P is the chance of going up and 1 minus P is the chance of going down, now I have to find out what would be the expected value. Expected is nothing but average. In probability terms, expected is nothing but an average. So, when we have done one of the calculations also in probability chapter, whenever we have to find out expected return or expected value, it's the probability multiplied by the corresponding value and adding up all the numbers, weighted average, right? So, here there is some probability that it will go to UUS, because it has to first go to U, then it has to again increase. So, 2 consecutive days of increase. So, first day increase is P. Again, second day probability of increase is P. These two are independent events. So, the probability of increasing for 2 consecutive days is nothing but, because they are independent, it's the product of their independent probabilities, P into P. So, there is a P square chance that it will touch UUS. It will go up on 2 days. Similarly, going down on 2 days, 1 minus P into 1 minus P, because it has to go down on both the days. Similarly, if I have to look at UDS, it could follow 2 paths. One is it could go up and come down, or it could go down on first day and it can come up. So there are 2 paths here. So the first path, the probability reaching in the first path is P into 1 minus P. The second path is also 1 minus P into P. So there are 2 paths. So the probability when multiple paths are there is like addition, because either it can go via path 1 or path 2, which is nothing but the addition rule of probability. So what I do is P into 1 minus P plus P into 1 minus P. So it becomes 2 into P into 1 minus P. So there is a P square chance that it will go to UUS. There is a 2 into P into 1 minus P chance that it will go to UDS. And 1 minus P whole square chance that it will go to DDS. So based on that, I should be able to find out what is the expected value. These kind of questions are very common. Sometimes they'll talk about the stock price. Sometimes they talk about the earnings per share, whatever is the term. If it talks about the probability of going up and down at various points in time, and the question is about expected value, all you are doing is finding out the probability from the starting point to each of the ending points, and then doing a weighted average to arrive at the expected value. So now let's look at the numerical corresponding to this. A stock is priced at 10. So the today's price is $10. 60% probability of moving up, 40% moving down. If it moves up, it increases by a factor of 1.06. So what is happening? The 10, it can either go up 10 into 1.06, which is making it 10.6, 10 into 1.06, or if it goes down, it decreases by a factor of 1 by 1.06. So which is nothing but 10 divided by 1.06. So what will be the value? So if I look at 10 divided by 1.06, 9.43. So there is some chance that it will go to 9.43. Now, we are also talking about what is the expected stock price after two successive periods. This is after one period. So again, after one more period, if I have to do, I am doing the same process. From 10.6, it can go up by 1.06. So this is becoming 10.6 into 1.06, making it 11.24. So this is 11.24. This is 10. You can work it out. 10.6 divided by 1.06. So which will make it directly 10. And whereas this one 9.43 divided by 1.06. So at 8.896 rounded up to 8.9, let's say. So these are the numbers, right? So after two periods, whatever is the period, after two periods, there is some chance that it will go to 11.24. There is some chance that it will go to 10. And there is some chance that it will go to 8.9. Based on this, I have to find out the expected value. So for expected value, I all need to know the values as well as their probabilities. So the values are, as we have pointed out, 11.24, 10 and 8.9. These are the values. Probabilities wise, how do I go to 11.24? Only one route. Up and up. Up is 60%. Two ups. So 60% into 60%, which is 36%. Right? 6 square. 60 square, 36%. Alright. Now, what about down? 40% and again 40%. 16%. So this is 16%. And the middle, which is going to UDS, two paths. One is 60-40, the other is 40-60. 60 into 40, 24%, 40 into 60, 24%. So 224%, making it 48%. Now look at, is it a probability distribution? First of all of them are lying between 0 and 1. The sum of their probabilities is equal to 1. So it's a probability distribution. So because this is a probability distribution, I can find out the expected value simply as the weighted average, which is making it 11.24 into 36% plus 10 into 48% plus 8.9 into 16%, giving my value 10.27. So the expected value after two periods is going to be 10.27%. Now on this, if we ask you to find out standard deviation, variance, all the calculations you can do. We have done similar kind of calculation once. Once this table is there, now standard variance, if you have to find out, from each value subtract the expected value, square, multiply it with its probability and add them up. That is what will give you the variance. Take the square root of that, it will give you your standard deviation. So just with a tree, he can give you a simple tree and he can even ask you to find out the expected values, and this will help us even at a later point, even in level 2, in terms of finding out, forecasting the stock prices, or even doing the pricing of options also. So the binomial tree movement is one of the important aspects that we need to look at in this process. Alright, so that is one application of binomial distribution also, because now if there are only 2 periods, there are only 3 final values. But if there are 20 periods, right, the same thing, I won't forecast just for 2 days. Probably I may have to forecast for 20 days. If that's the case, my tree would be a very lengthy tree, because from each there will be 2 more branches. It would be a very lengthy tree. Now, finding out how many paths are there. Here anyhow for the middle one I am saying 2 paths, because I am able to visually look at it. But the moment even the third one comes up, identifying number of paths will be very difficult. Right? Probably if I am looking at one more path from here, there itself the complexity starts. You see, if I have to reach here, there are multiple paths, up, down, down, or it could be down, up, down, or it could be down, down, up. There are 3 paths which are taking you to that same location. Now, you have to identify all the paths, and that makes it difficult also the moment the number of trees increase. That is where the binomial distribution formula will come into picture. NCX into P power X into Q 1 minus P to the power N minus X. Those many paths will be there. So even from that standpoint, the binomial distribution is typically applied. Of course, as far as the current exam and example are concerned, even if you are comfortable with the 2-stage tree, that is more than sufficient for us. Now, in this context, the next topic to be looked at is tracking error, which is very widely used in the world of portfolio management. Just nothing but I look at what is my actual return or expected return, whatever I am getting. See, I expect that I should get 10%, 12% based on the probabilities and all. As in the earlier example, we are expecting 10.27% return. If I expect that 60% it will go up, 40% go down, and 1.06 is the factor, then I am saying the expected return is 10.27%. Right? But actually, if it comes out to 11%, or actually it may come out to 9%. So the difference between the actual return and anything we have set as a benchmark, generally whatever we are expecting, we can set as a benchmark, or probably I can set, oh, I have to achieve at least 15%. It could be a very straightforward number, or it could be a calculated number, whatever it is. If I am setting something as a benchmark, any deviation from the benchmark is what we are calling it as a tracking error. Right? And sometimes as simple as this. Look at this calculation. Initially I am starting off with 100,000, ending up with 95,000. Manager's performance is measured against an index that declined by 7%. Whereas what happened to your portfolio's return? 100,000 has become 95,000. So there is a decline by 5%. Decline by 5%. The actual return is a decline by 5%, which is minus 5. Right? Your actual value was minus 5%. Minus, what is your benchmark value? Benchmark value has actually declined by 7%. So your tracking error in this case is as simple as 2%. You thought that your expected wise it should fall by 7%, but it has fallen only by 5%. So you have performed much better compared to the expectation. Now, why is this used is, I have to check how much accurate are my forecasts or my expectations. If they are deviating quite drastically, let's say you predict, yeah, this month I'll get 14% return, but you have generated, let's say, 18% return. Right? You have see, at the beginning of the year, any finance guy, beginning of the year, beginning of month, beginning of investment, there is some number in the mind of the investor. I should get this much versus how much did I actually get. The difference which I am looking at is what I am calling as a tracking error, because even if it is heavily positive, like I expect 14% but I get 18, 14 and 20, every time there is a big difference, then there is some problem with my estimate. Same thing on the other side. So sometimes people look at by what extent are the estimates fluctuating from the actuals also. So that's again an important aspect in the portfolio management theory. So that is where we capture this value of tracking error to see to what extent is the accuracy of the forecast with the actuals. So this is just a small piece of thing to be looked at. Application, another application of expected return kind of stuff. Now we move on to the continuous. So as far as discrete is concerned, for L1, only two major distributions are considered. One is your uniform distribution again there, and the second one being the binomial distribution. Whereas when it comes to continuous, again there are two itself. One is uniform, which is again a straightforward distribution. The other is a very key distribution which will be used across almost, called as the normal distribution. So these are the two key distributions that are used from a continuous distribution standpoint, right? In discrete as well as continuous, we had this concept of uniform distribution, right? Which is nothing but, when we said discrete, only finite values are there. Continuous, almost all values are possible and all of them have equal chance. Let's say I have a number between 1 and 5, and any number is possible between 1 and 5, not just 2, 3, 4. 1.1, 1.02, 1.03, all, any infinite numbers are there between 1 and 5, and I can pick any one of those numbers randomly, which means our application can allow any possible value. Then I cannot say it is discrete, because one, the number of outcomes are so large, the probability of each outcome is very minimal, and probably I am equating it to 0. Then I am calling it as continuous. So for a continuous, as we have discussed, we cannot have the probability function, but we definitely have probability density function, which is applicable for a range of values, not for a point. For a point, the probability is always 0 in case of continuous, whereas for a range, it exists. Now, when I am saying continuous uniform distribution, it's fairly simple. 1 to 5, let's say any value can be taken. Now I want to find out what is the probability that the number I pick up lies between 2 and 4. So overall possibility is between 1 and 5. So this is my range, 1 and 5. This is 1, this is 5. Any value is possible within this range. Now as a favorable thing, the person is asking, what is the chance that it lies between 2 and 4? Because the uniform distribution is nothing but all values have equal chance. So the probability in this case is a straightforward calculation, where I will take the difference of my favorable range So 2 to 4, the difference is 2. 4 minus 2. Divided by the difference of the total range. 5 minus 1. 4. So the probability in this case directly becomes 2 by 4 or 50%. In a continuous uniform distribution, it is straightforward because all of them have equal chance of occurring. So the simple way to find out the probability is take your favorable range divided by the total range. Range is nothing but maximum value minus minimum value. So you take your favorable range divided by the total range, which will give you the probability of occurrence. Look at this numerical. A random variable x is continuous, bounded between 0 and 5. Calculate what is the probability that it will lie between 2 and 4. How much is that? What is the probability that it will lie between 2 and 4? Favorable range is 2 because 2 to 4. 4 minus 2, which is 2 by total range. Total range is between 0 and 5. 5 minus 0, 5, which is giving me the probability in this case. Now look at the next one. Similarly, random variable follows a continuous uniform distribution over 27 to 89. Any value is equally possible between 27 to 85. What is the probability of an outcome between 34 and 38? Favorable range is 4 divided by total range being 89 minus 27. So 62, I think, whatever is the calculation. So 4 divided by 62 is your probability that it will occur between 34 to 38. So continuous uniform distribution, just you need to understand the basic concept. Even in case of discrete also, simple calculation. Probability, if there are n different outcomes possible, 1 by n is the probability of each outcome in a discrete uniform distribution. In a continuous also, because a point cannot occur, it's always a range. So the question would always be asked in terms of two ranges. One is the total range possible and one is the favorable range which you are looking at. So favorable range divided by the total range will give you your probability of occurrence. Now this is the key in the entire finance world. Most of the calculations that we are going to drive are going to be based on this concept of normal distribution. The way the graph of the normal distribution looks like is a symmetric, this is the typical graph of a normal distribution. And what are the key things for it? One, this is symmetric because this is where the mean, the median and the mode, all three are lying at the same point. One, that is giving you that the skewness is 0. Because if it is positively skewed or negatively skewed, we find that there is a difference between the mean, median and mode. Only if it is symmetric, we say all three of them are same. So one, it is symmetric means equal 50% to the left, 50% to the right, and there is a gradual fall. Skewness is 0, kurtosis is also 0, excess kurtosis. Kurtosis is equal to 3, excess kurtosis is equal to 0, which means there is a kind of gradual fall from the mean. And there is a single peak, which is mode is also at the highest point. Mode, mean, median, all three of them are same. Shape is typically a bell shaped. So because skewness is 0 and kurtosis is 0, the only parameters that are available for a normal distribution, because any data we said, it is defined by 4 characteristics. The central tendency, the dispersion, skewness and kurtosis. Now for normal distribution, we won't have skewness and kurtosis because both of them are zeros. Kurtosis means excess kurtosis. They both are zeros. So the only two things that are required or that are available for a normal distribution are mean and standard deviation. One is the central tendency, one is the dispersion. Whether you call mean, median, mode, all three are the same. So one is that central tendency and two is the dispersion, which is the most common form of dispersion is standard deviation. So when we define a mean, when we define a normal distribution, we just need mean and standard deviation of that, because the other two are directly taken to be zero. That is one key reason why many applications of finance use the normal distribution, because if I am able to compute the mean as well as the standard deviation, two things of a data, I can very well attribute the normal distribution feature to it. In case the data is following a normal distribution, I can really do the estimations and forecastings much appropriate. We'll look at that aspect. And skewness and kurtosis, excess kurtosis are zero when we talk about a normal distribution. So that is making it the key factor. A common, see, when we are looking at uniform distribution, the graph is more like a straight line because all of them will have equal chances. Whereas here in the middle the frequency is higher, and towards the left and the right the frequency gradually falls, and there is a tail. The tail means there are very few chances, the frequency, wide away from the mean, either to the left or to the right, there is a small possibility of occurrence in the value. Very small, it will not touch the x-axis at all, which means there is nowhere the chance is zero. There is a chance, but it could be 0.000001. As we go wider and wider and wider from the mean, it will not touch zero at all. So that's where I have put slightly above the horizontal line, because it will never touch. It's a kind of infinite. And as we have discussed, the area under any probability density function is equal to 1, because it's the sum of all probabilities. Sum of all probabilities, which will be equal to 1. So the area underneath this entire curve is equal to 1. So if the question is on what is the probability that some value is greater than something, it's nothing but 1 minus something. Because when we did in case of binomial distribution, right, what is the probability that the value is not equal to or greater than at least 1? Then we said we'll do for 0, or if there are 10 possibilities, we have to do it for 1, 2, 3, 4, 5, 6 and add them up. Or do it for 0, what is the probability of getting a 0, and subtract that value from 1. So which is nothing but the area under the entire probability function is equal to 1. So here also the entire area under the entire normal distribution function is equal to 1 itself. So once we take up a couple of numericals, that becomes even more clear for us. But yeah, you have to understand this distribution to the core to actually do a lot of problems in finance, even at a later stages. Now, a few offbeat stuff here. Sometimes we would be dealing with one variable or multiple variables together. For example, if I am focusing only on returns of one company, then I call it as a univariate. Only one company data I am taking, and I am trying to focus on the mean, standard deviation, all calculations of that one single company. But sometimes, I mean, we cannot look at investing only in one company. When we are using the word called portfolio, the main intention of a portfolio is combine one or more security, two or more securities, with an intention to reduce the risk. So when we are doing that aspect, we are looking at two different variables of data. Or probably if I have 5 different companies to form a portfolio, I am looking at 5 different variables. Infosys, Wipro, DLF, Reliance, whatever. I am looking at 5 different variables of data. So for that, what happens? One, I'll look at their mean, I'll look at their standard deviations, because every data is structured with all these possibilities. Then, if I have to combine them, I have to look at the interrelationship between those variables also, which is given by our concepts of correlation and covariance, interrelationships. Now, we also defined that correlation or covariance always exists pairwise only. Even if there are 5 companies to look at, A, B, C, D, E, the covariances are between A and B, A and C, A and D, A and E, B and C, B and D, something like that. So it's always a pairwise. Now if the number of variables are increasing, the number of pairwise correlations or covariances which I have to compute will actually go up drastically. So sometimes the question that comes out is, how many correlations I have to really compute if there are n variables, which is given by n into n minus 1 by 2, which is nothing but nc2. You can very well write this as nc2, which will work out as n into n minus 1 by 2. So if there are 3 variables A, B, C, I need to find out the correlation between A and B, A and C, B and C. All pairs. A, B, C, D. A, B, A, C, A, D, B, C, B, D, C, D. 6. Which is coming up as 3 into 3 minus 1 by 2. Right? Or 4 variables are there. So 4 into 4 minus 1, 4 into 3 by 2, which is working out to 6 itself. So the more the number of variables I am having, the more is the number of calculations I have to do, not just their individual means, individual standard deviations, but I should also end up finding out their pairwise correlations or covariance. Because if I find out the correlation, covariance is derived. Because covariance, or we have defined the formula the other day, correlation is covariance divided by the standard deviations of each of them. So standard deviations we anyhow are finding out for each of them. So correlation is, if I am able to find out the correlation, just multiply it with their standard deviations, which will give me their covariances. So sometimes the question would come out, how many parameters I have to capture if there are 5 variables. So if there are 5 variables, I would be computing 5 means, correct? 5 standard deviations and 5 into 5 minus 1 by 2 covariances. Because normal distribution requires only mean and standard deviation. Skewness and kurtosis are 0. Skewness and excess kurtosis are 0 for normally distributed variable. So only the first 2 things will be present. So I am finding out their means. So 5 means I have to find out. 5 standard deviations I have to find out. But because we are talking about multi-variables, there is an interrelationship between the multiple variables. So I have to end up finding out those many correlations or covariances also, which is another 10. So the question typically goes with finding out 20. Or sometimes people write it as 2n plus n into n minus 1 by 2. 2n is 1n is for means, 1n is for variances, and n into n minus 1 by 2 for covariances or correlation. Probably you could even simplify it. You can apply mathematics to simplify it, take n out of common, all kinds of stuff you can look at. This is the typical number of calculations that need to be done if there are multiple variables. But this is one more advantage with a normal distribution. If I see that 2 different stocks, let's say Infosys returns and Wipro returns, follow normal distributions each. This is a normal distribution Infosys. This is a normal distribution, let's say Wipro. Right? Individually. Now if I combine them, also I can create a normal distribution. That is one important property. That is what is a multivariate. If Infosys returns is a normal distribution, Wipro returns is a normal distribution, right? I can combine these two normal distributions to form a third normal distribution, and the only thing is I have to find out the correlation and covariances between the variable. That is one big fundamental of normal distribution, which may or may not work in case of other distributions. Probably if Infosys is a binomial distribution, Wipro is a binomial distribution, combining these two need not form another binomial distribution, right? But that's the unique property of normal distribution. Even if I combine multiple variables, it will still follow a normal distribution. That is one of the reason the whole world of finance or portfolio management gets driven around the concept of normal distribution itself. So the first thing anyone has to do before they build a portfolio is to check whether the returns of each of the securities are following a normal distribution or not, right? Just I'll try to show you a small demonstration if I get the data. Of course, this is not from a exam standpoint. Exam standpoint, just if you understand the basic characteristics of a normal distribution, that should be more than sufficient. Alright, so let me just try to get the data. Last 1 year data if I look at. Alright. Now let's say I'm looking at this data. Let me just close off the remaining stuff. So these are the prices of Infosys stock for the last 1 year, right? So I will take the returns of them. Return is nothing but the percentage change in the price. So I'll simply take it as this value minus the previous day's value. That is the change upon the previous day's value, which will give me the percentage change. So I am taking the percentage change for all the days, right? Probably I'll put it in percentage form. So these are the percentage changes. So this is what sometimes in your numericals in your exam, they are directly giving the numbers without giving the prices and all. If the returns are 0.12%, 1.88, find the expected return, find the average, all these kind of calculations which we have done in stats, right? So here I can do the expected return, the standard deviation, because these are data itself. So the mean, which is the expected value, which is a simple average of the numbers. So I am not again redoing that stuff. So there is an average of 0.04 and let's say standard deviation. Alright, the standard deviation is this much. Now I need to know whether this is normal or not. For that, I need to find out the skewness and kurtosis, if they are 0 or not. Of course, calculation of skewness and kurtosis is not in our scope of the exam, right? Only we need the interpretations part, but just showing, okay, skewness is 1.2, which is not close to 0. So probably these returns are not fully normal. Infosys returns for the last 1 year, if I am taking, they are not fully normal. If they are normal, the skewness should be very close to 0. Or even the kurtosis should be very close to 0, but it is showing 32. So which means there is a huge deviation. Of course, the way we address the deviations and all the remaining statistical aspects, we remove some outliers, we do a lot of juggling manipulations on the data. But what happens is, assume that this is a normal distributed return. That's how your exam comes. The real world is may or may not follow a normal distribution. Whereas your exam simply talks about assume that this is a normal distribution. Now in reality, I have various other mechanisms to make it normal. I'll remove some outliers in the data, I'll do some other stuff. That's a real practical world of doing it. Right? So here, if I am assuming that Infosys is normal and Wipro is also normal, same exercise. If I assume, when I say skewness is 0, kurtosis is 0, plus or minus some small difference is also still accepted. Like 0.2 minus 0.2, because in reality I cannot virtually create a 0. So if it, as long as it is very close to 0, both of them, I say that they are normal. Now when these two are normal, what I can do is, I can create a portfolio, 70% in Infosys, 30% in Wipro, or 60% in Wipro, 40% in Infosys, whatever. Some combinations I can create, which would also be a normal distribution itself. That's the unique property of a normal distribution. So based on which I can find out, I know now the shape. Even after Infosys and Wipro are combined, the shape is still a bell curve. So the projections become very easy. How do I project? Based on the shape, I'll know the area under the shape is still 1. Right? What is the chance that the value is greater than this much? What is the chance that the returns are less than this much? Because the area is 1. So greater than something, less than something can be easily found out even for a portfolio. So as we were discussing right from day 1, based on the data, if I can identify the shape, the estimates become very easy. Now individually I can find out the shape of these things if they are normal. But because of the unique property, even if I combine these two in some proportion, that will also be normal because of that unique property that is existing with the normal distribution. What we are able to do is, even for the portfolio, the graph is known. Even without we identifying the distribution for that. Because we have identified the individual distributions are normal, combination of them is also normal, which will give us the shape of the portfolio directly. Once we know the shape of the portfolio, any estimate, what is the chance that the return is greater than 12%? In one step I can do the probability. What is the chance that I'll lose on this portfolio? Just again, what is the area under that normal distribution curve? It's a straightforward. We'll take up a couple of numericals that makes it more and more easier in terms of understanding this concept. Now, this is where we define the intervals. We have already said that this is the normal distribution, right? This is the mean, some standard deviations to the right, some standard deviations to the left. We have used the Chebyshev's inequality in our first chapter, which said what proportion of the values lie between plus or minus k standard deviations from the mean, which we said as 1 minus 1 by k squared. Now, that is irrespective of any distribution. So, if it is 2 standard deviations in that example itself. We said it is minimum of 75% of the data will lie. 1 minus 1 by 4, 3 by 4. 75% of the data will lie between plus or minus 2 standard deviations. But in case if it is a normal distribution, you will find minimum of 95% of the values. Not even 2. Within 1.96. These are standard values. So if I say this is 1 standard deviation this side and 1 standard deviation this side. Between these 1 standard deviation this side and 1 standard deviation to the right, you will find approximately 68% of the values. That because there is a peak and a gradual fall. So based on that gradual fall, what has been arrived at is around 68% of your data, if it has to be normal, around 68% of your total observations should lie between plus or minus 1 standard deviation of the mean. Similarly, few more standard values are given. If I am talking about 90% of the values, they lie between 1.65 standard deviations from the mean. So when the question is about build a 90% confidence interval, which means confidence interval is nothing but the interval within which the value can lie. Because see, I'll give a simplified version of that. I'll ask you a question. How much return, right? Or probably how much can India score tomorrow's match? If you say 250, that's like a point, dot. Probably you should be a god or a baba to tell that. Right? India will score 250 tomorrow. My question will come out as, are you really confident about it? Or what is your confidence? Now, or sometimes we use, can I believe it? Right? Can I trust on that? Now the next step a person will say is, yeah, 240 to 260. Right? Then how much confident? 50% I am sure that it will lie between 240 to 260. But I want more and more guaranteed, more and more confident stuff. Then you will say 220 to 280. The interval keeps widening. The more and more confidence I have to impart to my estimate, the interval gets widened. I want that interval. Right? That is what we call as the confidence interval. When the data is following a normal distribution, it's 90% sure, 90% of the values, whatever we are talking of, 90% of the scores will lie between plus or minus 1.65 standard deviations. If I take all the scores which India has been scoring over the past 100 matches, simple. Over the past 100 matches, I am taking the scores of India. Right? And if I could see that it is following a normal distribution, means there should be skewness of 0, kurtosis of 0, excess kurtosis of 0. If I am able to see that that data is following a normal distribution, now I will find out the average. Probably let's say if average score is 250 and standard deviation is 20. Just for assumption. Now what I can very well conclude is 68% of the times they have scored between 230 to 270 because average is 250. Between plus or minus 1 standard deviation, there are 68% of the values. So 68% of the scores are between 230 to 270. If it follows a normal distribution only, right? If it does not, then it could be, then it has to go with the Chebyshev's inequality. Two standard deviations, which is 210 to 290, because 250 is the average, 20 is the standard deviation. So when I say two standard deviations away from the mean, it is 210 to 290. What we can very well say is, between two standard deviations, at least 95% of the values, because 1.96 standard deviations only, which is close to 2, almost 95% of the values are lying, which means 95% of the India scores are lying between 210 and 290. That is giving our, see, now the question may come up, what is the chance they will cross 300? Probably try to apply it to the stock market world also. If I find that the returns are following a normal distribution, I can very well say 95% of the data, 95% of the returns will fall between mean minus 2 standard deviations to mean plus 2 standard deviation. Now if I want it beyond that, let's say mean is 0%, right? In our example itself, let me assume that this is the normal. Where is this? Yeah. Let me assume, forget about these two things for time being. Assume that this is normal. Mean is 0.04. Standard deviation is 0.019. Now, what is the 2 standard deviation here? This is the 2 standard deviation. So, if I take mean minus 2 standard deviation, which is this much, mean plus 2 standard deviation, this is this much. Now what I am saying, in 95% of the days, Infosys will give a return between minus 3.77% to 3.85%. Now if someone says, what is the chance it gives more than 5% return on a day? Just imagine there is a question, can I make 5% return in a day? You know, 95% it will lie between these two only. So if he has to make 5, which is beyond this, there is a very small chance. 95% lies between these two. So 5% is beyond minus 2 standard deviation this side and plus 2 standard deviation this side. Again symmetrical. So 2.5% to the left, 2.5% to the right. That too, I am not asking about above 3.85. If it is above 3.85, directly I may say 2.5%. But he is asking above 5. So it could be even less than 2.5%. Probably the exact values will come out from normal distribution tables. But just to give a simple ballpark number, I may say no, it cannot be more than 1%. Right? May or may not be more than 1%. So you making a 5% profit in a day is not more than 1%. So that is how the normal distribution is used in the probability world. Now, sometimes the banks, they actually calculate what is called as value at risk, which is nothing but what is the maximum amount they can lose in a particular day, right? Because of whatever aspects. Now, I know that 95% limits are this much. So, there is only 2.5% chance, 2.5% chance that my return will be less than this number. Return is less than 3.77 means my loss is more than 3.77%. There is only 2.5% chance that my loss is more than 3.77% in a day. So for every 100, I can lose $3.77 only in 2.5% of the cases. Remaining 97.5% of the cases, I will not lose that much. It's a very important aspect to actually plan my money, because I cannot lose more than 3.77. 96.23 is more or less fine. Only that 3.77 is the possibility of my loss, is the amount that I can lose. So if I take some kind of measures for that, it actually addresses my risk management problem also. So that is where identifying the patterns of the distribution and based on that computing the probabilities makes a bigger and bigger applications in finance. Right? Of course, we don't need to get into those calculation aspects today. That's how your advanced finance will come into picture. But just understanding the application of where this normal distribution would be used. So as far as normal distribution is concerned, if he is giving in a question, these four, it's better to remember. If the question is about build a 90% confidence interval, you simply say mean plus or minus 1.65 times the standard deviation. Then 95% is 1.96 standard deviations and 99% is 2.58 standard deviation. These are very common questions that are there. So just look at the question here. If X has a normal distribution with a mean 100, standard deviation 5, what is the 90% probability range? 90%. So mean minus 1.65 standard deviation to mean plus 1.65 standard deviation, which will be made as 100 minus 1.65 into 5, which will make it, I think, 8.25 to 100 plus 8.25, which is making it as 91.75 to 108.25. So what is that I am saying here? There is a 90% chance that this value will lie between 91.75 to 108.25. Right? In 90% of the cases, this is a very important concept as far as sampling also goes. The next chapter is on sampling. Lot of numericals of sampling also, they go with the same fundamental. Right? We will use the same concept again there to actually do the estimation based on the sampling or even the hypothesis testings also. So as far most of our questions are related to normal distribution, whether it is a hypothesis testing chapter or most of the chapters, they go with the assumption of normal distribution, because most of the data in the real world today, most large amount of finance data also in the real world follows a normal distribution. So just from that standpoint, it's better to understand almost all the characteristics of the normal distribution. Now let's try to look at the next numerical. This is what is a key one. A portfolio manager is looking at an investment. Expected annual return of 10%, which is mean. Mean is 10%. Expected is average. 10%. Standard deviation of 5%. Assume the returns are approximately normally distributed. This is how it gives. What is the probability that the return will exceed 20% in a given year? What is the probability? How do I express 20 in the form of mean and standard deviations here? How do I express this 20 in the form of mean and standard deviation? Mean is 10. Standard deviation is 5. Right? So it means, yeah, I'm coming. This is the mean. Mean is 10. Standard deviation is 5. So this is 15, mean plus 1 standard deviation. Mean plus 2 standard deviations is 20, right? Standard deviation is 5. Mean plus 1 standard deviation is 15. 2 standard deviations is 20. Similarly, mean minus 1 standard deviation is 5. Mean minus 2 standard deviations is 0. These are what are numbers. Now we know it's a normal distribution. So between minus 2 standard deviation to plus 2 standard deviation, almost 95% of the values are there, approximately, because 95% 1.96 rounded up plus 2. So 2 standard deviations from the mean, approximately 95% of the values are there. So as this graph is concerned, between 0 and 20, the area between 0 and 20 is 95%. And because of the symmetric nature, the area between 10 and 20 is 47.5%. Because normal distribution is symmetric in nature. So to the left there is a 47.5. To the right of the mean there is a 47.5. But what is our question? Exceed 20%. Exceed 20% is even beyond the 20% limit. Right? 10, 15, 20. I want more than 20. What is the chance? So up to 20, between 10 and 20, it is 47.5%. Above 20, it's the remaining 2.5%. Right? Because it's a 50% to this side, 50% to the other side. So if the question is about what is the chance that it goes above 20%, I'll say it is 2.5%. Now tell me, in the same question, what is the chance that it will go above 15%? Sorry? 45? Above 15%. Yeah, up to between 10 and 15, it is 34%. Right? Because 68%, one standard deviation, the total is 68%. One side, 34%. I want it above 15%. So the remaining area is 16%. So there is a 16% chance that the returns will cross 15%. Getting it? What is the probability that the returns will lie between 15 and 20%? What is the chance that the returns will lie between 15 to 20%? 13.5%. Because 15 and above, it is 16%. Correct? 20 and above, it is 2.5%. I want it to lie between 15 to 20. So out of this 16%, the remaining, this 2.5% should not be applicable. So I can directly say 13.5% chance that the returns will lie between 15 to 20%. That's how the questions are framed. So you have to be very much comfortable between these 4 data points. Intervals wise, if it is a normal distribution, 1 standard deviation 68%, 1.65 standard deviations is 90%, 1.96 standard deviations, if he says build a 1.96% interval, you have to just say 95% interval. You are just doing 1.96 times standard deviation and plus or minus to the mean. Same thing with 99%, 2.58 standard deviations. So this is a very important slide as far as estimations are concerned, because you are giving a range to your numbers. So even in our Infosys data case, I am saying there is a 95% chance that the Infosys returns will lie between minus 3.77% to 3.85%. So anything beyond that you require, it's just the remaining 5%. So when someone has to make some statement and either accept that statement or reject that statement, this percentages will help us out. Right? If someone is saying no, Infosys will give 5% return, there is a very less weightage to it. There is a very less chance that it will be, that will occur, because our data is saying 95% of the observations should lie between minus 3.77 to 3.85. So when you are making a statement, Infosys will give 5% return, the chances are less than 2.5%. I may not even believe your statement. I'll say I'm rejecting your statement. Because I am sure 95% is between these two. Getting it? That's how we take the advantage of our calculations to make our conclusions on the data. Now, the normal distribution, there is one small variant in the normal distribution called as standard normal distribution. See, what happens is, in our normal distribution earlier, we have taken the mean as 10, standard deviation is 5. So there could be different means and different standard deviations existing. What people have done is, they have standardized that normal distribution. That is what is called as a standard normal distribution. What happens in the standardized form is, the mean is always 0. Not 10, 20, no number. Mean is always 0. Standard deviation is always 1. So, mean plus standard deviation is nothing but 1. Mean plus 2 standard deviations is 2. Similarly, mean minus standard deviation is minus 1, minus 2. So, actually the x-axis looks like 0, 1, 2, 3, minus 1, minus 2, minus 3. That is what is nothing but your standard normal distribution. Now, how do I convert the existing normal distribution into a standard normal distribution? All you have to do is, from every value, subtract the mean and divide it by the standard deviation. It becomes a standard normal distribution. Subtract the mean from every value x, you subtract the mean, divide it by that standard deviation, which will make it a standard normal distribution. Just look at this example itself. If I want for 15, what is the standard normal value, or what is the standard normal value corresponding to 10? From 10, subtract the mean, which is 10 itself. 10 minus 10, 0. Divided by the standard deviation. Whatever it is 0 itself. Right? 0 by 5, 0. Okay, so in place of 10, it becomes a 0. Now look at 15. Subtract the mean. 15 minus 10, 5. Divide by the standard deviation, which is 5. Makes it 1. So this is nothing but 1 standard deviation from the mean. This is 2. 20 becomes 2. 20 minus 10, 10. Divided by 5, 2. So what is happening is, any normal distribution can be made into a standard normal distribution by subtracting the mean and dividing it by the standard deviation. Now, because of this, what comes out is, this 1, 2, whatever the numbers are, they are nothing but your number of standard deviations. So 95% of the values will lie between plus or minus 1.96. I don't need to say 1.96 standard deviations anymore, because the x-axis is 1. Each standard deviation is 1. So that becomes constants now. 68% of the data lies between plus or minus 1. I don't need to say standard deviations anymore, because it's in a standard form, where standard deviation is equal to 1. 95% of the data will lie between plus or minus 1.96. So I can even say the lower limit for 95% of the data is minus 1.96, the upper limit is plus 1.96. Right? That is the standard normal distribution. So there is nothing much different between a normal and standard normal. But terminology wise and notation wise, people talk about Z. Z distribution, whenever they say, it is nothing but standard normal distribution. It's just the same normal distribution itself, but with a specified thing. Mean will be 0 for that and standard deviation will be 1 for that. Those kind. So any normal distribution can be converted into a standard normal distribution by applying this kind of a fundamental. And the calculations of the probabilities or percentages and all remain the same. Just like the way we have done how much above 2 standard deviations and all that, here also we'll do the same kind of calculation. Look at this numerical here. Monthly sales of hot water heaters, approximately normally distributed, mean is 21, standard deviation is 5. What is the probability of selling 12 hot water heaters or lesser? So convert it into a standard normal distribution, each of the numbers. What is the mean? 21. But I have to convert it into a standard normal. So I will make it as subtract the mean from it and divide it by the standard deviation, which will make it 0. Now what about 12? If I convert it into a standard normal, how much it will be? 12 minus the mean, minus 21. 12 minus 21 comes out to minus 9, divided by the standard deviation, which is 5. Or probably for our simplicity purpose, let's make it 4.5. So minus 9 divided by 4.5, which is minus 2. So minus 2 will be somewhere here. So that value is nothing but minus 2, standard normal value. Subtract the mean divided by the standard deviation. So the Z value in this case is minus 2. So now what is the question? What is the probability of selling 12 water heaters or lesser? So which is less than minus 2. This is the area he is asking for. So what is the area? How much is this area? 2.5%, because minus 2 to plus 2, 95% approximately, right? So again symmetry. So 0 to minus 2, 47.5. Below minus 2, 2.5. Where in the question? It's a normal distribution. Every normal distribution can be converted into a standard normal. There is no difference between a normal and a standard normal. The only thing is it's like a it's like a transformed. Both are one and the same. There is no dilution in the value between a normal and standard normal. In case of normal, we are saying 1.2 standard deviations from the mean or 1.96 standard deviations from the mean. But when we are using standard normal, we won't use that word called standard deviation from the mean, because we are already standardizing it. So whatever is the way you are doing, whether you convert it or you don't convert it, the result is one and the same. The question is on 12 heaters or lesser. So 12 in standard normal form is getting translated to minus 2. Right? Because the average is 21. In a standard normal form, it is getting translated to minus 2. So minus 2 or lesser. Minus 2 to 2, we know the value. See, so if I had not made it 4.5, if I had kept it as 5 itself, what was your value? 12 minus 21, minus 9 by 5. Minus 1.8. Correct? So it would have been somewhere here. we directly don't know the number corresponding to 1.8. Probably I have to refer to the normal distribution tables and something like that. He will not give the tables in the exam. In the exam, if required, he will give the value corresponding to 1.8, but he will not supply you the tables. So most of the questions in the exam, they will surround around these four values itself: 68%, 90%, 95%, 99% kind of values itself to a large extent. Otherwise, he expects you to do some kind of approximated value. See, he'll give, let's say if it is 1.8 itself, if it calculates as 1.8, you'll know what are the answer choices he'll give is, if he still gives 1.8, you don't know what is the value corresponding to 1.8. So he'll give the answer choices: A 40%, B 14%, C 20%. What would be your answer? Assume that he has given as standard deviation of 5 only, which has in your standard normal form it got translated to 1.8, or probably let me make it sorry, this let it be 20%. This I'll make it as 4%. What would be your value? If the calculation has, you're getting my point, right? If the, let's say your standard normal calculation has come out as minus 1.8, but you don't know the value, the percentage corresponding to 1.8, because you only know corresponding to 1, 1.65, 1.96 and 2.58, which are for those four, 68%, 90%, 95%, 99%. Now if the calculation comes out as 1.8, he expects actually you to do an approximate calculation, because the actual values will not be given to you. So he expects some kind of approximation. You know, corresponding 90% means 1.65. So your minus 1.65 should be somewhere here. So minus 1.65 and below, it is 5%. Because 90% means symmetry. 5% to the left, 5% to the right. So minus 1.65 and below is 5%. But I want minus 1.8 and below. So it would be slightly less than 5%. So 4% could be my calculation. So without actually doing a calculation, I need to do some kind of approximations there. So once I know the clarity between these four calculations, it becomes easy for me to do all these kind of computations. Look at the next one. Stock return normally distributed, mean of 16%, standard deviation of 50. What is the probability of a negative return in a given year? So here the answers also I'll give, because without answers this becomes difficult. So this is 40%. This is 60%, and this is 20%. What is the answer in this case? So look at what are the values, that makes it easier. So what is the mean? Mean is 0, standard normal. What is the standard normal? What is that? I have to find out probability of a negative return. So which is below 0. Negative return is nothing but below 0. So what is the value corresponding to 0? What is the z value corresponding to 0? 0 minus mean divided by the standard deviation, which is 0 minus 16 divided by 50. So minus 8 by or minus 16 by 50 minus 0.32. So minus 0.32 lies somewhere here because 0 is in the middle. Minus 0.32 somewhere here. I want this area. So obviously it will be less than 50%. So the option B is removed. Now it could be 40 or 20. Now we know for 68%, which is 34%, right? Plus or minus 1. So minus 1 and below it is 16%. I need, so it cannot be 20%. It could be much higher than 20% itself. Right? Minus 1 and we are talking of minus 0.32, which is very close to 0 rather than 1. So it cannot be close to 20%. Probably much higher because the area that is left out is a very small area. Out of the 50%, very small area is left out, which cannot be more than 10%. So approximately you are marking it as 40%. So that's the way some numericals will be worked out. Without giving you the table, he expects you to compute the percentage on a trial and error basis. So obviously the options will be on a simple elimination basis itself. So you should be able to eliminate the option choices to mark them correctly. Yeah. Now one more concept in this context is the Roy's safety first ratio. It's actually called as the Roy's safety first criteria ratio, which it says is it's more similar to your Sharpe ratio itself. In a Sharpe ratio we said excess return per unit of risk. Here also excess return per unit of risk. The only difference between these two concepts is in Sharpe ratio we subtract it from a risk-free rate of return. Whatever is the return which you are getting minus risk-free rate of return divided by the standard deviation. Whereas in case of safety first criteria ratio, we don't look at the risk-free rate of return, we look at a target return. So my benchmark need not be risk-free, right? Probably some other company's performance or my benchmark performance. Probably as a company I need minimum of 10% return. Anything above that I am fine. So the main difference between a Sharpe ratio and a safety first criteria ratio, interpretations are one and the same. The higher the ratio is, the better it is for investment, because for a lesser risk or for any one extra unit of risk I am taking, I am getting excess return. So higher the value, the better it should be chosen for investment, whether it is in case of Sharpe ratio or safety first criteria ratio. The point is, any portfolio which I am choosing, which is having the highest, the safety first criteria ratio or the Sharpe ratio, probably is the one that should be included into my investment criteria. Right? That's an easier way to look at whether it is using a Sharpe or using a safety first. There is no difference in the interpretation. The only thing is calculations are different because one is based on risk free, assuming even without taking any risk I am getting this much return. So how much excess return I will get if I take 1 unit of additional risk. Whereas here, okay, even if you don't take any risk, I want you to generate this much return. Target. Now, taking your excess risk, if you are generating anything more than that target, that is the most preferred kind of an investment for me. So, the major difference between these two, and This also follows a normal distribution criteria, which will tell me what is the probability that it will fall below a particular value. The same logic. Now let's say my target is 10%, normally distributed. What is the chance that my return falls below 5%? If the standard deviations, okay, see, my target return is 10%. Standard deviation of the returns is 5%. What is the chance that my portfolio value will fall below 5%, less than 5%? So now as far as my normal distribution is concerned, my average is 10%. So I'll convert it into a standard normal distribution, which is 0. And what about the 5%? What would be the standard normal value for that? If this is the mean and this is the standard deviation, what would be the Z value for that? Minus 1, because 5 minus 10 divided by 5. Minus 5 by 5, which is minus 1. So I am asking about what is the chance that the value is below 5%, which is below minus 1. Below minus 1, what is the area? 16%. 68% between minus 1 to plus 1. So there is a 16% chance that my portfolio will give me 5% or below. And some other portfolio I will try to find out. If it is having only a 5% chance that it will fall below minus 1, or that it will fall below 5%. 5% return. Here there is a 16% chance that my portfolio's value would be, or portfolio's return is 5% or lesser. Probably if I look at some other investment, if there is only 7% chance that the portfolio's value falls below 5%, that is a better investment. From a risk standpoint, there is a 16% chance in this that I will lose, or my value, I will gain only 5% or lesser. Whereas in the other case, there is only 7% chance, which means 93% chance that my return will be greater than 5%. Getting this? Whereas in this case, there is only 84% chance that my return will be greater than 5%. So obviously 93%, if I am going with an assured kind of stuff, I would prefer a 93% confident kind of an investment compared to a 84% confident kind of an investment. So that's how the investment with higher safety first criteria ratio would be preferred. Whether it is Sharpe or safety first criteria, the difference between the two is the safety first criteria even will give you the probability that it will fall below a particular value. That is what we call as the shortfall risk. What is the chance? What is the probability that your value will fall below a particular number? Right? What is the chance that you will lose? Lose means 0. So the standard normal value for that is minus 2. 0 minus 10 by 5. Minus 2. So what is the chance that you will lose is nothing but what is the chance that the standard normal value will be less than minus 2. 2.5%. Right? So most of the calculations related to the normal distribution, the expectation, once you know those 4 numbers, you should be able to solve the questions. Tracking error is only, it does not divide it by your standard deviation. It's an absolute dollar value. Like I have estimated 5%, but it has given 7%. So 2% is my tracking error. But it is not taking into consideration for each unit of risk. So there is only the numerator part in the tracking error. Tracking error divided by the standard deviation is what is my safety first criteria ratio. But just because I am dividing it by standard deviation, I am bringing it into a limit. Because the tracking error, I may estimate 5%, but it may give me 40%. 35%. There is no way I can interpret it. But here I cannot give probabilities there. But once I divide it by the standard deviation, I know that it is following a normal distribution pattern, which will help me to give the percentages or probabilities in terms of value going below a certain value or above a certain value. So, which is nothing but it is one standard deviation away from the mean, which is getting above 1. There is only 16% chance. See, if this is becoming 1, means the return is 15%. If the return is 15%, 15 minus 10 divided by 5, which is working out to 1. So, safety first criteria is equal to 1. In the normal distribution, where is 1 occurring? Here. In the standard normal distribution, 1 is occurring somewhere here. Above 1, there is a 16% data. Below 1, there is a 84% data. So, there is a 16% chance that I will get more than 15% return, and 84% chance that my return will be less than 15%. So, there is no higher value. Higher value in sense, it falls into that scope of normal distribution. Probably there could be 2, it could be 3, but whatever is the value, the only thing I can say is beyond that, what is the chance? Below this, what is the chance? So, the shortfall risk, which is what is the chance that the value will fall below this much, is what I am defining as a shortfall risk. And wherever the shortfall risk is lesser, which means I will not lose more than this much amount, which is what is the confidence level from an investor's standpoint. So, the higher is the safety first criteria, I am actually coming to the right. If the safety first criteria is higher and higher, I am actually coming to the right in this normal distribution. So, which is which is enhancing my chances of actually losing. So, I will not lose to a large extent. If my safety first criteria is going up and up and up, I'm actually not losing, I'm actually gaining off. So, the more it goes to the higher the safety first criteria, my chances of losing are going down and down. Yeah, here normal distribution is one thing which we have. Normal distribution is one thing which we have looked at. There is a slight variation to the normal distribution, which is called as the log normal distribution. What is the difference between these two is, see, normal distribution as we have seen till now, it's more symmetric in nature. Equal to the left, equal to the right. Which means there is a possibility of negative values as well as positive values also. When I say 2 standard deviations from the mean, minus 2, minus 3 are all possible. Whereas in reality, some numbers may not accept negative values. For example, prices, stock price. On the higher side, it can go to any amount. But on the lower side, it cannot fall below 0. So, what happens for very small securities, when I have to create a symmetry about the mean, if let's say the average stock price is $10 and standard deviation is $5, minus 2 standard deviations to plus 2 standard deviation is 0 to 20. Symmetry. Minus 3 to plus 3 is minus 5 to 25. 25 is very much possible to exist, but minus 5 cannot exist for a stock price, which means it cannot follow a normal distribution, because if it has to follow a normal distribution, it has to be symmetric. Symmetric means equal number of values should be there 3 standard deviations toward this side as well as 3 standard deviations toward this side. Towards the right, the 3 standard deviations are very much possible. 25 is the stock price, which may be possible also. But minus 5 is a stock price which will never be possible. So it is definitely not a symmetric distribution, especially the prices. Not the problem with the returns. Returns could still be on both the sides. I may get negative returns, I may get positive returns. So returns wise, they will still follow normal distribution. But prices will not follow normal distribution, especially the entities which are capped on the downward side at 0, especially the prices. Prices or sales volumes, the sales cannot become negative. At the max, it can go to 0. At the worst case, it can go to 0. So there is a capping on the left hand side. So wherever there is a capping on the left hand side, which means it's like a skewed distribution, right? It is more skewed towards the right because highest side any value is possible, but on the downward side there is a cap. So the typical graph may look more like this, which is nothing but your right skewed kind of a distribution. So this kind of distribution, which especially is used for prices and sales kind of data, is what is being called as a log normal distribution. Now, why am I calling as log normal distribution? If I take the logarithms of each of the values, logarithm of the prices, right? Logarithm, later on we'll come to know the logarithm of the prices is nothing but the returns. We'll prove that slightly later. But the logarithm of the return of the prices is nothing but the returns. But even without knowing that relationship, if I look at the logarithm of the values, that will follow a normal distribution. If the values don't follow a normal distribution, look at their logarithms. If the logarithms follow a normal distribution, then we say the actual values are following a log normal distribution. That's the difference between these two. The values as such, they don't follow normal distribution. The moment I take the logarithm of each of the values, they follow a normal distribution. Now, what is the measure of that normal distribution? Again, as we said, skewness should be 0, kurtosis should be 0. That's the stuff, right? When I take for the original prices, it will not follow a normal distribution. But the moment I take the logarithm of each of the prices, right? Instead of taking 100 price, I take log 100, whatever it is. 2, 3, 4, whatever is the number, log 100. Like that, 200 price, make it log 200. Now that's a new data. That data, if it is normal, I say the original data is log normal. Especially in the finance world, to model the prices, stock prices, lot of assumptions relating to the stock prices are assumed to follow a log normal distribution. So that's one thing we have to be comfortable with, especially where the boundaries are fixed on the lower side. At least it cannot go negative. Any variable whose value cannot go negative. As returns does not follow log normal, returns follow normal. As far as finance is concerned, these two things, if you remember, it's good enough. Prices follow log normal distribution. The logarithm of prices, which is nothing but returns, we'll come to know slowly. The logarithm of the prices, which is returns, they follow normal distribution. That is the relationship between these two distributions. If each value I take the logarithm, and after taking the logarithm of each of the values, it becomes a normal distribution, then I call that as a log normal distribution. And the shape of the log normal distribution is more like a right skewed kind of a distribution, right? Because negative values are not possible, and on the left they are bounded with 0. Some of the basic concepts, if you are aware, that should be comfortable. log normal prices are returns. Returns can be negative. So when I take the logarithm of the data, I can get negative value also. The logarithm of the data as such, I can get a negative value also. But the actual value, there cannot be negative. Right? See, okay. In this Excel sheet itself, as I am saying, the logarithm of the prices is the returns, right? Instead of taking the difference between the prices, I'll take the division of the two prices. The logarithm can still come out as a negative value, and both of them are one and the same. If you see, if I round it off to 2 decimals, whether I do the today's value minus yesterday's value divided by yesterday's value, the difference in the values divided by yesterday, or even if I take the logarithm of today divided by yesterday, the values are one and the same. Right? So whether I take the logarithm or difference divided by the original value, both will give me the same calculation. So this is what I meant by logarithm of the prices is my returns. Returns are following negative values also, but prices are showing positive values. So prices will follow a log normal distribution and returns will follow a normal distribution in this case. Right? Then this is one offbeat aspect, simulation, which is more like the moment I know the parameters like average and standard deviation. Let's say I know these two values. I want to generate the data back. See, till now you take the data and on that data you compute the mean, standard deviation, blah 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 stuff. But sometimes what happens is the data that is available to us may be very small. Probably last 4 months, 5 months, 10 months kind of a data only is available. Or sometimes what happens is someone has supplied us the data, saying not the data, the parameters. The mean of the distribution is 5% with a standard deviation of 2%. They did not give us the actual data. They have given only these two things because summary can very well be shared. Now using these two, if I have to construct the data back, I'll depend on Monte Carlo simulation, which is nothing but using the two parameters or whatever are the parameters, mean, standard deviation, whatever are the characteristics given. Based on that, using the concept of random numbers, and you know that it is a normal distribution, based on these two information apart from mean and standard deviation, once you know that it is a normal distribution or any distribution for that matter, normal distribution, and use some random numbers. There are so many tools that generate random numbers. Even Excel also generates random numbers, which is just, if you see, there is a formula in Excel called rand. Nothing. It gives some number. Every time that number changes. Randomly it gives some number. So we are all talking about random variables only till now. The data occurring randomly in nature. So which can be generated through this concept of random numbers. Now using these two inputs, I can create a data which is more normal in nature. Now just I am telling you what I would like to demonstrate there. Someone has given me that the mean height of the people is 170 centimeters. and standard deviation is 10. Only these two data have been given to me. Now I want to find out what percentage of people. Now look at it. I have got the data saying the average height is 170 centimeters. Standard deviation is 10 centimeters. Just using these two, I want to find out what percentage of people lie above 200 centimeters. Right? So one way is I can generate the sample. How do I generate the sample? That is what simulation will help me out with. So if I simply say, of course, we don't need to generate it. This is done only by the computer systems. So I'll use some random numbers with a mean of 170 and a standard deviation of 10. I'll ask the system to generate a random number. Some height has been generated, 165. Now I'll generate so many such things. I did not do anything. Randomly, now it's as if I have gone to 1000 people and gathered their heights. It's as if, now you see the numbers here. Randomly, they are generated, these numbers. But you see, they will follow a normal distribution with a mean of 170 and standard deviation of 10. Now let me try out the mean, which is I am taking the average. Approximately you will get those numbers itself. 169.92, which is close to 170. I did not do any work, right? Which is I wanted a normal distribution. That's it. Now look at standard deviation of this. 9.87, almost 10. Right? Skewness. This is like a backward calculation. Using the parameters, generate the original data. Almost 0. Minus 0.12. Earlier, when with the real data, when I have actually captured it, it was 1 point something. This is very close to 0. And kurtosis, very, very close to 0. All of them are very much satisfying that this data is a normally distributed data. Now, once this data is normally distributed, I can find out how many of them are lying above 200. So I'll simply use some kind of a formula which says how many of them are greater than 200. Just demonstrating it to you, you don't need to bother about this. So there is only one out of probably 1000 or whatever the numbers I have simulated. Collecting 1000 data is very difficult. Rather than that, just by using a 30 or a 40 or a 50, if I am able to compute the mean and the standard deviation, I can very well use those two numbers to generate large samples and based on that find out the proportions going below or above kind of stuff. And that is where this simulation today is a very important aspect in the world of risk management. Because not every instance can be found in my historical data. Right? Not every instance. Let's say I am taking a last 1 year data. It may not be possible that 10%, minus 10%, all data is very much possible in that. It may not be possible. Some extreme events may not be possible in the last 1 year data. But if I am doing a simulation using these parameters, I can even try to get how many, see again in the same example, if I go to 50 people and take their heights, I may not get anyone who is above 200 centimeters. Right? But that doesn't mean that the height never falls above 200 centimeters. So simulation from the parameters will really help us in trying to generate all possible values in a random fashion. So that's where we are saying used to produce the actual data using the concept of random numbers and by assuming their distribution. So any complex problems today, whole world of risk management uses this concept of simulations itself. Risk management, derivatives, these kind of worlds, they depend very heavily on simulation. But of course, this becomes fairly complex the more and more variables get introduced. If there are, is here we have generated only one height. But if height, weight, combination has to be generated, then it becomes a fairly complex kind of a scenario. That's one limitation of it. And the accuracy of the numbers will be based on the assumption of your distribution. If you assume that it is a normal distribution, the data is generated as per normal distribution. If you assume that it is a uniform distribution, the data is generated as per uniform distribution. So, based on the correctness of your assumption regarding the distribution, the values are generated. So, there is a human dependency there. The distribution which you are assuming, the correctness of the distribution will define the correctness of your data also. And one more type of simulation which people depend on is historical simulation. Here I won't calculate the mean or the standard deviations. I look at the old data. Okay, in the old data, there was a 3% increase. There was a 3% fall. Yesterday, there was a 4.2% increase. Day before yesterday, there was a 3.1% fall. All possibilities that are there, that have happened in the last 1 year, 30 days, whatever is the period I am considering, I assume that all of them are possible with equal probability. So, which means, if some event has occurred in the past, then only it has relevance for the future. But if that event has not occurred in the last 1 year, historical simulation will fail to capture that. It's as good as saying, in last 1 year, let's say earthquake has not occurred in the city. So forever, because I am using historical simulation to forecast the future, last 1 year data which I have considered, there was no earthquake, so in future no earthquake. That's a historical simulation. But the Monte Carlo simulation looks at the mean as well as the standard deviation in the values, and based on that, probably it may say 0.0001% chance of an earthquake occurring rather than a 0. That's the difference between the two. Because it has not occurred in the past, it may not give any value for the future. So if it's as good as saying, if there was no return, if there was not even a single day where the loss was 5% in a day, in the last 1 year data which I have observed, my historical simulation will say that I can never lose 5% or more. There is a possibility always. Probably that the chance could be 0.001, but it cannot be 0. One possibility could come out that I may lose beyond 5% also. But because I did not lose beyond 5% in the scope which I have considered for analysis, it will tell me that in the future also I will not lose more than 5%. But what the Monte Carlo simulation does is, okay, it is understanding the pattern. Based on that, it's saying it's not 0, but it could be much, much lesser. So because it is generating the values randomly, which will follow that kind of a pattern. So in that random generation, probably when I have generated 5,000 such random samples, probably 1 or 2 out of those 5,000 could be beyond 5% limit. So it means that the chance is not 0, but it could be 0.002, something. That is what will bring out the accuracy in our assessment, rather than just looking at the limited set of values. So that people sometimes do historical simulation also, just generate the probabilities based on what has occurred in the past, or a Monte Carlo simulation which is based on understanding the distribution, the pattern of the distribution, the mean and the standard deviation and the other parameters of the values. Fine.